Okay, this podcast is an introduction to electrochemistry, or using chemistry or chemical reactions to do work. Okay, so if we just think about what happens, let's say if we take a strip of zinc and we put it in a solution, let's say of copper sulfate, a copper solution that has copper ions, what you'll see happen is the copper will actually plate out and coat the zinc. So these copper ions are coming out of solution. They are picking up 2 electrons that are coming off the zinc, and they are plating on the zinc strip as copper atoms. And they turn brown as they do that. And the solution gets lighter because there's fewer copper ions. So in this case, we have a loss of electrons or oxidation by the zinc, and we have copper being reduced by adding of electrons and becoming copper atoms. And so these are redox reactions, and we can use this reaction, which is spontaneous, to generate electricity. And this is basically the basic chemistry of how a battery works. So let's take a look. Alright, so here is what's called an electrochemical cell. It is sometimes called a galvanic or a voltaic cell. You basically have 2 strips of metal, different metals that act as anode and cathode, and a wire where we allow this flow of electrons to occur, and it measures how much energy is being produced in volts. Volts is a measure of joules per charge. We have these electrodes in these solutions. We have the salt bridge that is there to balance charge. So let's take a look. If you didn't watch the podcast from Khan on galvanic cells, you should watch that. It explains how these work and how the electrons flow as a result of these redox reactions. Just a little bit of terminology. We have both oxidation and reduction going on. In the case of sodium, it is losing an electron. And in the case of chlorine here, it is gaining electrons and becoming negatively charged. So this is a reduction. The charge goes from 0, it goes down, it's reduced. And oxidation is the opposite. The charge goes up in that process. A good way to remember which is which is the saying Leo says Gur, a loss of electrons is oxidation, and a gain of electrons is reduction. Okay, a couple other pieces of terminology. One is oxidizing agent. The oxidizing agent is the substance that is being reduced, because the process of it being reduced, let's say it's gaining electrons, allows the oxidizing agent to do its thing. Okay, so by gaining electrons and being reduced, it's accepting electrons from this other metal, causing that to become oxidized. So they work in reverse. It can be a little bit confusing. You just got to get it straight in your head. Reducing agent, therefore, is the substance that is oxidized, because these don't happen in isolation. One material has to be oxidized while the other is being reduced. So they have to work in pairs and in concert with each other. Okay, we also have the anode and the cathode, and those are the plates that are hanging out of those beakers. It's the electrode where the oxidation actually occurs is the anode, and the cathode is where the reduction occurs. Now, the great memory device for remembering this is red cat. Remember the red paw? Red cat. Reduction occurs at the cathode. And the other thing you need to remember here in this word cathode, think about the T as being a plus sign. The plus positive electrode is the cathode. So the positive is the cathode. Reduction occurs at the cathode. So on the back of your periodic table, you'll see the standard reduction potentials. And these are, this is the table that you'll be allowed to use on the AP test. But they are listed in terms of the potential number of volts that are released in comparison to hydrogen as a standard. So the hydrogen is allowed to be reduced here, and then everything else is reduced, and the voltage comparison is made. And that's what this table is. So the reaction on this list that produces the most voltage when being reduced is the fluorine here, and the voltages go down as you go down the list. So the closer you are to the top of the table, the more likely this element, when it's in a reaction with another, is going to be the one that is reduced. Okay, so you see positive values, and then you go down to increasing negative values. Alright, so we can measure standard electrode potentials. Here we have a galvanic cell. Again, potentials are measured against hydrogen, which is arbitrarily set at 0. And here we have zinc metal that is losing electrons. Electrons flow through the wire and back into the, in this case it's the platinum, it's an inert electrode. Reactions that occur in electrochemical cells are spontaneous by definition, which means they produce a positive number of volts. So they are spontaneous, positive cell potential, and they also have a negative free energy, which also indicates that they are spontaneous. Here we have a zinc and copper galvanic cell. We have a zinc metal here. And this zinc loses electrons in this reaction, oxidation reaction. And those electrons travel through the wire. This is a flow of electrons, which is known as electricity. And they reduce this copper. And as it happens, the copper picks up the electrons and becomes copper metal. So it's blue in solution, picks up the electrons, and actually becomes that coppery color, and will attach itself to this electrode. So this electrode will actually gain mass as these coppers are reduced, and they form the additional layer right on the copper metal. We can look at the table of reduction potentials for zinc and for copper. And now this is an oxidation reaction. When we turn it around, we get the reduction reaction. And what we see is the reaction for zinc. This is this one turned around. Zinc 2 plus 2 electrons gives us zinc metal is negative 0.76 volts. Copper plus 2 electrons gives us copper. This is the reduction reaction, and it gives us a potential of 0.3 volts. Okay, so we know that not both metals are going to be reduced, so we have to think about which one is going to be reduced and which one's going to be oxidized. And the more negative or the less positive the value on that table, the more likely that element is going to be oxidized as opposed to reduced. So the higher it is on the table, the higher the positive value, the more likely to be reduced. Okay, so zinc is lowest on the table, it's the most negative. So what we're going to do is we determine that this is not going to be reduced, it will be oxidized. Copper will be reduced. So we're going to turn this around and change the charge. And when we do this, we end up with positive 0.76. We add these together and we get a cell potential. This naught means standard cell potential of 1.1 volts. We can draw this line notation for an electrochemical cell, and the way we do this is if we start on the left here where we're being oxidized, we draw the zinc, the metal that's being oxidized, the metals in solution, the ions in solution form from that. And then on the right hand side we have the Cu2+, the ions in solution here, and then the metal on the outside. So we have the anode material, the anode solution, the cathode material solution, and then the cathode material. Those are line notations which you need to know how. Alright, let's take a look at this problem where we have to describe what's happening in a cell. Let me make my pen blue. Okay, so here we have this redox reaction going on. It's spontaneous, which means it's going to produce positive volts. We have potassium dichromate in sulfuric acid in one beaker, potassium iodide in another, salt bridge used to join the beakers. Metallic conductor that will not react with either solution is suspended in both. So here's a anode and a cathode that are platinum, which will not react, just serves as a conduit. And the two conductors are connected with wires through a voltmeter. Alright. The resultant voltaic cell generates an electric current. Indicate the reaction occurring at the anode, the reaction at the cathode, the direction of the electron migration, and the direction of ion migration, and the signs of the electrodes. Okay, so let's draw a cell. So, best to do it in two beakers, right? I'm not the best artist, as you know. I have two electrodes. They are both platinum. Those electrodes are going to be connected to a voltmeter where electricity will flow through. I need to have a salt bridge. I'll explain the purpose of the salt bridge in a second. Alright, now I like to put the anode on the left. And if you remember red cat has a positive sign, and it's where reduction occurs. So that means the anode is going to be the negative, the cathode will be the positive. This is where reduction occurs. This is the cathode. The opposite is where oxidation occurs. This will be the anode. Okay, so now we've got to figure out which is going to be where. So it's easiest for me to look at what's happening with iodine here. There's also something happening with chromium, but let's just look at the iodine. The iodine goes from I minus to I2. So this side is going to need electrons. So it is losing electrons. So it is oxidation. Okay, so the oxidation is going to occur here. I'm going to go from I minus to I2 plus electrons. Okay, and over here I'm going to have the chromium 2, let's say, that looks like it's going to be a plus 6 going to a, and adding electrons and going to a chromium plus 3. Okay, so when this happens, what I'm going to have is iodine in solution that's going to give up electrons, right? And those electrons are going to come over and get picked up by the chromium. Okay, so what's going to happen here is I'm going to have these, I have this iodine solution here, I think they said it was potassium iodine, and it is going to give up electrons. Electrons are going to flow up here, right, and flow through the wire, and flow down here and get picked up by this Cr plus 6, right? And that Cr plus 6 is going to become Cr plus 3. This I is going to become, lose electrons and become I2. Okay. So that's where the reactions occur. Now it's asking about what's happening in the salt bridge with the ions. Now the salt bridge is there, and it's often potassium nitrate. So it's there as potassium ions and calcium and nitrate ions, and it's there just to balance the charge, because if we started running this battery, it's going to run down pretty quickly, and we want to have a continuous running battery. So we have to decide where we need the positive ions and where we need the negative ions. So as we are on this side, the negatives are going away. So what we need to have happen is we want the positive ions flowing this way. Oops, wrong thing. I want the negative ions flowing this way, because the negative ions are going away and becoming neutral. So I want to replenish the negative charge to the negative, and I want my, that should be NO3 is flowing this way, and my potassium is going to be flowing this way because I want to replenish. The Cr plus 6 was becoming plus 3, and I want to replenish and get it back to the positive. So just using the salt bridge to balance. So the NO3 again in the bridge, I'll redraw the bridge. The NO3 ions are going to go towards the iodide, and the potassium is going to go to the right. Kind of a mess, but that's the way it's going to work. Okay, so we can calculate the reduction potential from the cell potential. Okay, the net cell potential. Alright, so we have this zinc copper 2 plus voltaic cell, and we have this redox reaction going on. The entire cell potential is 1.1 volts. And in the table, if I look it up, zinc plus 2 to zinc is minus 0.76 volts. So it says calculate the reduction of Cu2 plus to Cu. Okay. So what it is saying is this is gaining electrons, so this is being reduced, and the zinc is being oxidized. Okay, so this is being reduced. It's got to have a more positive volts. Okay, and therefore the zinc is going to go the other way. So the zinc will go from zinc solid to zinc plus 2 electrons, and we'll reverse this charge to be plus 0.6. Alright, so the whole thing is going to be 1.1 volts. The difference here has to be this, which is going to be 0.34 volts, and that's going to be the Cu2 plus 2 electrons gives me Cu. So it's kind of some simple math once you figure in your head what's going on. Okay. Calculate the standard EMF for a cell that employs the following overall reactions. So let's write the half reactions. We have aluminum going to aluminum 3 plus, right? We have iodine 0 going to iodide negative. Only 2 of those. So we need electrons on this side, and I'll need electrons on this side. Okay. So I am losing electrons here, and this is going to be oxidation, gaining electrons. This will be reduction. Leo the line says GR, right? Alright. So let's take a look at the cell potential table. So if I look at it, aluminum, you should look for it at the same time. Aluminum, it says aluminum 3 plus 2, aluminum is 1.66 to the negative. So if I'm switching the reaction around, it's going to be 1.66 to the positive. And then iodine, it says I2 gaining 2 electrons is so it says I2 plus 2 electrons to 2I is 0.53. So the cell potential is the combination of the two. So it's going to be 2.19. So the table's a little different than the table in the book, so that's why it's not quite exactly the same. And that would be volts. Alright, so let's take a look at this one here. So we have a voltaic cell based on the following two standard half reactions. Cadmium plus 2 going to cadmium, tin plus 2 going to tin. So cadmium plus 2 is minus 0.40 volts, And 10 plus 2 is going to be, let me see, 10 plus 2 is going to be minus 0.14 volts. Alright, so this is lower on the table, this is higher on the table, this is less negative, so this is going to be my reduction. Okay? That's just the way it works. The one that's got the highest reduction potential is going to be reduced. This is lower, so it's going to, I'm going to switch the reaction around, it's going to become my oxidation. So CD is going to become cadmium 2 plus 2 electrons, and that will be a positive 0.4 volts. So the overall is going to be the difference, which will be 0.26 volts. Okay. And it wants to know which is the cathode and the anode. So, okay, so here I am gaining electrons. That's GER, reduction. Losing electrons, that's oxidation. A red cat, reduction, occurs. This is at the cathode. And what occurs at the anode? The anode is going to be not this, but this. And that looks consistent with the answer key. Okay, so we're going to stop this right here.